Hello everyone, welcome back to the YouTube channel. Again, my name is Rukumi S. Sabana from ECE31, and for today's episode of our Power Electronics Laboratory, we will be having experiment number 4, or our half-wave rectifier circuit with RL source load and inductor source load. For our objectives, we aim to simulate the half-wave rectifier with RL source load using Pspice software. Second is to utilize the software to observe the behavior of half-wave rectifier with RL source load, and lastly, to determine the power quantities using Pspice software. So we just have to follow the procedures by constructing our circuit. So let's go to our Pspice. So using our Pspice, we have to create a new project, and then let's rename it experiment number 4. Okay, experiment number 4, and then my surname, and then we have to click analog or mix 80, and then we have to browse here, and let's select our folder for Power Elecs Lab, and then let's click OK, and then let's create a blank project. So let's just wait for it to load up, and after that, this will be the space for our schematic. So let's construct our circuit as shown in this procedure. So we will be needing a resistor, an inductor, and a voltage source. So let's go back to our Pspice. So in this part, we have to place part, and then let's search for our resistor. Okay, so let's place a resistor here, and then we will be needing an inductor. Okay, so let's place an inductor here in series with our resistor, and then we will be needing a diode. Okay, so we will be needing a diode here, and of course we need an AC source. So let's use our VC AC source. So let's place Pspice component, and then let's search here, and then let's type this in. So let's use this one for our circuit, which is a transient sine voltage source. So let's place it here, and then we will be needing a DC voltage supply. So let's exit this one, and then let's place Pspice component, and then source, and then our voltage source, and then our DC voltage source. So let's put it here. So let's press escape. So let's now zoom our circuit here. So we will be connecting our components through a wire. So our voltage source here, and then our diode here, and then our resistor here, and our inductor here, and our DC voltage source, and then our VSIN as our source will be connected to our DC voltage source here. So this will be our circuit for our part 1, or our RL source load. So we will be setting the values for our resistor. So our resistor will be 2 ohms, so just minimum value, and then our inductor will be 20 millihenries. Okay, and our voltage and our DC voltage source will be 100 volts DC. So let's edit here, 100 volts DC, and then our AC source here will be. So now, taking note of our AC source here, which is composed of 220 VRMS at 60 Hz. So since our given here, or our settings here, and our Pspice is V amplitude, okay, as you can see here, we will be getting the peak value of the VRMS voltage. So to get the peak value, we must multiply 220 to the square root of 2, and multiplying it, we will be getting a value of our peak amplitude, which is equals to 311.127 voltage peak value. So we will be considering that value. So after that, we will be considering a 60 Hz voltage source, and then our, I see. So this should be 0, okay, but the frequency will be 60 Hz, and then our voltage offset will be 0. So that's our circuit for this part of our experiment 4. Now this time, we will be creating a new simulation profile. So let's name this experiment 1. Okay, experiment 1 RL source, and then after that, let's create, and then let's just wait for it to load up. Okay, so as you can see here, there will be our update button here, which indicates that our simulation profile will be functioning already. And now, after setting our simulation profile, there will be a pop-up here wherein we will be setting our simulation to time domain transient. So let's click it here, and then we have to set the runtime. Okay, so the runtime to 16.67 ms. Okay, or if you want to convert it to seconds, that will be 0.1667 or 0.01667, or for easier typing, you can type 16.67 milliseconds, and then our start saving data will be 10 microseconds. So let's type it here, 10 microseconds here, and after that, that will be for 1 period of the source. So now we will click apply, and then click OK here. So on our step number 5, we will be performing transient analysis, and we will be displaying the average power by entering this expression in our Pspice. So let's go to our Pspice again, and let's run our simulation here. So before we run our circuit, let's place some ground here so that there will be no floating nodes on our circuit. So let's place a wire. So the other end of our voltage sources will be connected to the ground. So after this, we will be running our simulation, and again there will be a pop here, Okay, so let's just maximize our screen for our simulation, and then we will be plotting. So now we will be adding the trace of our average power, wherein we have to add trace here, and then we will be considering the power across our R1. So let's just find it here. Okay, so we have to click WR1 here, and then let's type average, and then let's have open and close parentheses for our expression. So let's click OK. So as you can see, the green waveform here is the average power across our resistor 1. So now, this will be the waveform for our average power absorbed by our resistor, which is our resistor 1, in series with our inductor and with our diode. So to get the peak value of this waveform, which is the peak value of the power across the resistor, we have to turn the cursor on, and then let's drag here our cursor to the peak of the waveform here. So as you can see, we will be recording a 971.798 watts if we will be considering the peak value of the power across the resistor. But if we will be considering the average power, or the total average power absorbed by our resistor, we have to measure it up until the end of the waveform. So here on the end of the green waveform. So if you will be considering it, we will be measuring a 556.833 watts for the average power absorbed by our resistor. So now after that analysis, we will be adding another trace, which is the average power absorbed by our DC voltage source. So now let's find it here. So this will be the average power, and let's find an expression here for the average, or let's just type it here for our convenience. So average, and then close and open parentheses, and then let's add its trace. So as you can see, the red waveform here is our average power across our voltage source. So from our circuit, we are able to output these waveforms, or we are able to output the power waveform for both the resistor and for our voltage DC source, wherein our voltage DC source is being supplied with the voltage from our AC source. And if you can notice, our average power output waveforms didn't start to rise instantly from zero. So it starts to rise at this point. So it's not literally from our zero starting point here. So to remind us, this half-wave rectifier circuit uses a resistor, an inductor, and a source load, which is connected to a diode here. So taking note of the role of a diode in a half-wave rectifier circuit, or let's say in a circuit, the voltage will not be supplied to the circuit or to the other components if the diode is not forward biased. Taking note of the role of diodes in our circuit, it acts like a switch. So if the diode is not forward biased, then our circuit, or the voltage source, or the voltage being supplied to the circuit, will not be given or will not be supplied to the other components, meaning there will be no current flow, or we can consider a minimal current flow in the circuit, which is sometimes not recognizable. So technically speaking, the components will not conduct unless our diode or our switch is on, or our diode is forward biased. So that's the common logic for that. So to better understand this, we have to add another trace, which is the voltage, okay, which is the voltage across our diode here. So it will be, so what is being recognized by our diode will be our voltage source from our AC source. So let's graph our voltage, our waveform for the voltage flowing across our diode. As you can see, it will be our yellow waveform here, which is starting from our zero initial point down to the end of our average power. And then to better understand this, let's add another trace, which is the voltage across our DC source. So it will be V1 VDC here. So that will be our blue line here, which is the voltage across our DC source load. So if you can see here, so this is the voltage across our diode, or our voltage AC source, and then the blue line will be our voltage across the DC source. So technically speaking, as long as the voltage from our AC source or the voltage across the diode is less than the voltage to our DC source, it means that the diode will not start conducting, meaning there will be no average power recognized or obtained from our circuit components, which is our resistor and our voltage DC source as well. But when the voltage across our diode or the voltage AC source starts to be greater than our voltage from our DC source, it is noted that there is a significant rise in our power output waveforms here, meaning the circuit starts conducting, the diode has been turned on. Okay, so literally, for example, in basic terminologies, the switch is turned on the circuit, meaning there is a current flow, and when there is a current flow on the components of the circuit, there will be power across our loads, or there will be power across our resistor and across our voltage DC source. So that's the logic behind that. So technically speaking, on this part of our graph, wherein the AC voltage source is less than the DC voltage source, the diode does not turn on and the circuit does not conduct. So there is no power reading. But when the AC voltage source is equal or starts to be greater than the DC voltage source, our component starts to conduct. So there is a power reading. So that point wherein the AC voltage source and the DC voltage source equals in value, that is what we call alpha here. So as you can see here on our graph or on our site output waveforms here, so this will be the point wherein our Vs and our voltage across the DC will be meeting on a certain point wherein they will be both equal. So in that case, our circuit starts to conduct. Now, to understand another parameter on our output waveforms, let's add another trace, which is, so now we will be adding the trace for the power or the average power absorbed by our inductor. So let's find it here. So this one. So let's just enclose it with parentheses. And then after that, let's plot it. So as you can see, the pink waveform here is the power across or absorbed by our inductor. So now understanding the beta here, which is another parameter in our circuit. So let's go back here. So here, on the average power across our inductor, when it reaches the zero mark here, that's our beta, wherein the current flow will be equal to 0, meaning the power absorbed by our components will be 0 as well. So to summarize this one, our the diode will be turned on, or the circuit will be start conducting when the AC voltage source will be equal to the voltage DC source, or will be greater than the voltage DC source. So that's the summary for our part 1. Now, for the part 2 of our experiment number 4, we will be having inductor source load, wherein we will just be having a diode, and we'll just be having inductor, diode, and voltage DC source as our loads. So now let's go to our Pspice, and then we will just be removing our resistor here, and we will just be. So with this, let's just put a wire here on the circuit, and then let's go back to our PDF. So we will be setting the values of our inductor to 20 millihenries, and then our VDC 200 volts, and then we will be considering the same value for our AC source here. And our site relation settings will be the same and identical to our part 1. So let's go to our workout here, and then our inductor will be 20 millihenries, and our voltage DC source will be the same, which is 100 volts. So now for our maximum step size, it will be 10 microseconds, and then now we will be performing transient analyses for the RMS current and power absorbed by our DC source. So let's go back to our Pspice, and then let's run the simulation here, and then let's go back to our simulation tab here. Let's just maximize it. So now plotting the RMS current of our DC source. So let's type it. Let's type here RMS, and then the current across our voltage source here. So let's have the open close parenthesis here, and then let's click OK. So this green waveform here is the current or the RMS current across our voltage DC source. So let's turn the cursor on, and then let's measure the peak value of this waveform here, which gives us 29.229 amperes, which gives us the peak value for the current across our DC voltage source. But when we want to measure the average or the current across our voltage DC source, this will give us 23.114 amperes here. So that's our current across our voltage DC source. So now to add a trace of our power across our voltage DC source, so let's go here, and then let's click this WVDC here. So as you can see, this is the power across our voltage DC source. Now let's turn the cursor on, and let's measure the peak value of the power across our voltage DC source. So as you can see here, the peak value is 4.404 kilowatts for our peak value of the power across the voltage DC source. So now to further explain this waveforms and our circuit, or our rectifier circuit, let's add another trace. So let's try analyzing the voltage across our voltage AC source. So this red waveform here is our voltage AC source, and then let's add another trace, which is our voltage across our DC voltage source. So let's find the voltage across our voltage DC. So as you can see, this is the voltage across our DC source, which is limited to 100 volts. So this sinusoidal waveform here implies that the voltage being provided is an AC voltage. So as you can see here, the current is being maintained. So that's the role of our inductor and our. So as you can see here, let's turn on the cursor. The current across our voltage DC source here, which is the RMS current, is just limited to a value. Okay, it's just limited to a value of 23.114 amperes. So this explains the role of inductor in a circuit. Okay, because inductor or inductance is the property of an inductor to oppose any changes in the value of the current. So notably, the impedance of inductor in an AC circuit is greater than the DC. This caused the RMS current across our voltage DC source be regulated or be maintained to a minimal value, but not approaching 0. Okay, take note that the inductor in an AC has a high impedance than it is on DC, thus maintaining a regulated value of current, okay, across the load, but not literally turning the current to 0, just maintaining a regulated value of current across the circuit. That's the role of inductor as our load, together with our DC voltage source load. Now let's add the power across our DC voltage source here. So let's find here, so power, and then let's click OK. So as you can see here, the yellow waveform is the power across our voltage DC source with a peak value of 4.403 kilowatts and an average value of 37.197 watts. So as you can see here, the rules or the observation we are able to take note from the part 1 of the experiment is applicable as well in here, wherein the power across our load, which is a voltage DC source, does not start literally from our initial point here, which is 0. It only starts after this intersection of our voltage AC source here and our voltage from our DC source. So it just started to rise on this point wherein our AC voltage source equals our DC voltage source or becomes greater than it. So this is our explanation for this. Now, this has the same concept wherein our average power here started to rise, meaning there is a noted flow of current to our circuit down to our voltage DC source, and then it falls down here again 0 when there is no current flowing on our components. So to have a better understanding, let's add another trace, which is the average power across our inductor connected to our voltage DC source. So let's get it here, and then let's just put a parenthesis on our expression for it to run, and then let's run it. So as you can see here, let's zoom it. So as you can see here, this is the average power across our inductor, which is the pink waveform here, which is landing on the same point with our power, across our DC voltage source. So zooming in our waveforms here, as you can see, they are landing on the same point here. This is the power across our voltage DC source, and then the power across our inductor. So now, since the power across our inductor landed on the same time with the power across our DC voltage source, let's now add another trace to check if the power across our DC voltage source will be the same with the power that will be supplied by our AC voltage source. So let's go to our power here, and then let's input our power across our voltage AC source. So zooming out our waveform here, as you can see, the mint green colored, or cyan, the cyan colored waveform here on our screen is the power from our AC voltage source, which is supplied to our DC voltage source, as well as our inductor. And as you can see, they all landed on the same specific point or same period of time on our graph, meaning this explains that the power that will be possibly supplied by our voltage AC source will be equal to the power absorbed by our inductor and the power absorbed by our DC voltage source. So technically speaking, since we considered the average power value of our inductor here, there will be a minimal loss, there will be a loss on the system since we didn't use an ideal diode and an ideal inductor as our components. But technically speaking, the logic is the same, that once we selected an AC voltage source, the voltage supplied will be distributed to the components, which is connected to in series with our voltage source, which is, as you can see here, the diode is connected in series with our inductor and with our voltage source. This means that the current will be the same all throughout the components, and at the endpoint, which is here on the voltage DC source, the power that will be supplied by this voltage here, which is an AC, will be equal to the power which will be received by our voltage DC here, regardless of the inductor here. But considering our inductor, there will also be a power absorbed by our inductor here. So there will be a minimal differences with the power absorbed by our inductor and the power absorbed by our voltage DC source here. But again, explaining, they will be all landing on the same specific time and point here on our time duration. So as our last test, we will be considering the average power of both of the voltage sources. So let's plot the average power across our voltage AC source. Okay, so let's type it here, and then let's plot it here. So let's just modify the equation by putting it on the positive cycle of our waveform. So in our trace expression, let's add a negative sign here. So let's click OK. And this will be the mustard yellow waveform here will be our average power across our AC voltage source. Okay, take note of it. And then let's add another trace, which will be the average. Okay, the average power across our DC voltage source to prove that most of the power which is supplied or possibly be supplied by our AC voltage source will be the same to the power. Will be the same to the power absorbed by our DC voltage source. So now adding the trace for the power across our DC voltage source, which is the average power. The pink waveform here is the average power across our DC voltage source, which is noticed or observed that both our average power from the AC voltage source and the DC voltage source landed on the same specified point or time duration in our waveform here. So as you can see here, both of the waveforms landed on the same point. So here on this part. So now let's measure. Okay, let's measure the the average value of this two average power, which is the average power from the DC voltage source and the average power from our AC voltage source. This gives us this gives us 1.57 1.57 kilowatts, which is the average power across our voltage DC source. Meanwhile, the average power for our voltage AC source will be 1.64 kilowatts. So this is different, okay? Both are different with a minimum value or minimum percentage difference because notably in a circuit, there will be a possible loss. Okay, there will be a possible loss across the diode, across the inductor, which explains the minimal difference of the average power of our AC voltage source and our DC voltage source. So if the circuit is ideal, then it will be equal, okay? But again, there is no perfect circuit and there will always be a possible loss across our components. That explains why the values are not exactly the same, but are near to each of the numerical values in our graphs. So this experiment explains while there is a possible loss on our circuits, specifically power loss, because we didn't use ideal components such as the diode, the inductor, as well as our voltage sources. So that's the end of our experiment 4. I hope you enjoyed, and let's proceed to our conclusions. As our conclusion, using our Orchid Light software, we are able to measure the value of the total and average power, as well as the RMS current of a half-wave rectifier circuit with an RL source and inductor source load. Power will only be delivered to load when the circuit conducts, implying that the diode is turned on or forward biased on the experiment circuit. Moreover, when the AC voltage source equals or becomes greater than the DC voltage source, the circuit conducts because the diode turns on or becomes forward biased. Otherwise, when AC voltage source is less than the DC voltage source, the diode is reverse biased or off. Additionally, the experiment on the half-wave rectifier circuit with the inductor source load proves the role of inductor, which regulates the current across the circuit with its inductance by opposing any change in the value of the current flow. Meanwhile, the measured average power across a DC voltage source has a near value to the average power across the AC voltage source with a minimal percentage difference in value, which signifies a loss in the system because an ideal diode is used in the circuit. Overall, half-wave rectifiers with inductor source load circuit will be essential to current regulated devices which needs a maintained current across the circuit. So that's our experiment number 4. Again, I am Rikami S. Bueno from ECE31, and I hope you learned something from our episode for today, and I hope I will be having you on our next video episodes for power electronics. So see you